We're very happy to have Arun Kannan from MIT, and he's going to talk about the center of a quantum group.
All right, yeah, thanks for having me. So last time we introduced the quantum group and then talked about its representations. Today we're going to describe the center of the quantum group, UQ of G. And so, as always, we like to draw analogy to the classical picture, where we look at the universal enveloping algebra of a semi-simple Lie algebra. And so one can determine the so-called Harish-Chandra homomorphism from the center into invariance of the symmetric algebra, wild group invariance of the symmetric algebra. And so for the quantum world, or the quantum side of things, there's a kind of a similar statement. And so our approach is going to be trying to mimic what happens in the classical case as insofar as much as we can, but there are going to be stages where we need some modifications. Okay, so with that being said, let's just recall some notation from last time about semi-simple Lie algebras. So hopefully this is all familiar stuff. I'm not going to spend too much time here. So for the purposes of this talk, we're just going to assume that K is a field of characteristic 0 and Q is an element of the group of units of K, and it's transcendental over the prime subfield. And so this is kind of a technical thing that we'll talk about later, but more importantly, it's not a root of unity. Okay, so G will be a semi-simple Lie algebra over C of rank L. U of G, it's enveloping algebra. H, Cartan subalgebra. Capital Phi, a set of roots with respect to your Cartan. Pi, a system of simple roots. And we'll usually denote these alpha 1 through alpha L. And then we have our positive roots, which denoted with a plus. These give you your triangular decomposition. The wild group, which acts on H dual, it's generated by the simple reflections, and W invariant inner product on H dual, where the convention is to take short lengths having length 2. And then the weight lattice, which we refer to the fundamental weights as omega 1 through omega L. And we have the dominant integral weights in the weight lattice. So the co-root pairing, weights whose co-root pairings are integers, that are positive, non-negative integers. This rho, which is the sum of the fundamental weights, and finally S alpha, which will denote the reflection associated to a root alpha. Okay, so that's just recalling some notation. So now let's actually just briefly recall what happens in the classical case. So this is kind of the second section here. And so to start, I'm going to define the Harish-Chandra homomorphism. So your Lie algebra G has a root space decomposition, and so you can think of this as a Z phi grading, and so this induces a Z phi grading on the universal enveloping algebra. And so we can refer to the piece with degree 0, elements consisting of degree 0 by U of G sub 0. And in particular, this thing will contain the enveloping algebra of H, because the Cartan consists of degree 0 elements, and also the center. And that's because if you act with that, so this gradation comes from the adjoint representation, and so you're going to pick up a factor if your degree is not 0, and so it can't be central. Okay. So U of G0, well, let's say this. We can define this two-sided ideal, U of G0 intersect U of G n plus. So it's an exercise to check that this is the same thing as U of G0 intersect n minus U of G, and that this is a two-sided ideal. And what you end up getting is actually this thing is complementary to U of H in U of G0. So we have the direct sum.
Maybe you could just write the statement that L is a two-sided ideal.
Yeah, okay. So is a two-sided ideal. So that's important because it's complementary to U of H as a subspace here, and so it gives you a projection map, and because it's a two-sided ideal, this is actually an algebra homomorphism. So you get a projection map, which we're going to denote pi bar from U of G0 to U of H. So let's box that. Okay. So the next step in defining the Harishchandra homomorphism will be we want to define this so-called twist of U of H, or a shift of U of H. So associated to each alpha I in your simple set of simple roots, you have a SL2 triple HI, EI, HI, and FI. And so in particular, the HIs, they form a basis of H. And so by the PBW theorem, the monomials in these HI, they will form a basis of U of H. So we can define the following algebra automorphism from U of H to U of H on these by requiring that gamma of HI is equal to HI minus 1, gamma of 1 equals 1, and then you extend it to monomials so that it's an algebra homomorphism. Okay, so that lets us define the Harishchandra homomorphism. So definition.
Would it be possible that you write that gamma is an algebra homomorphism?
Sure. So this lets us define the Harishchandra homomorphism, which is just the composition of these two maps. So I'm going to denote that with psi. U of G0 to U of H given by psi is equal to gamma composed with pi bar. Okay, so this is the definition. I want to make one more comment before I state the theorem in the classical state setting, which is, as I
but usually Harishchandra homomorphism goes from the center.
Yeah, so we'll talk about a restriction of this in the theorem, the restriction to the center. And so what we have is we have an action of the Weil group on H dual, and so this induces an action on H and hence on U of H. And since H is an abelian Lie algebra, this can be identified canonically with the symmetric algebra. And so we have an action of the Weil group on the symmetric algebra here, and so we can define the Weil group invariance in here, which is just the fixed point set under this action. Okay, so now let's actually state the theorem. So you have the following theorem. The restriction of psi to the center, ZU of G, is an algebra isomorphism from ZU of G to this symmetric algebra invariance. Okay, so the purpose of this talk is not to prove this statement, so I'm just going to give a very brief outline, and so that as we go through the proof in the quantum case, we have kind of this blueprint, or at least an idea of what is going on, what happens in the classical case. So it's clear that this is an algebra homomorphism, so that was something you can check, but this is an algebra homomorphism. So it just suffices to show that the image is correct, and that we have a bijection. So the next thing you can do is you can check injectivity. Now, usually this sort of argument uses some sort of central characters approach. And you can basically show that if Z in the center is sent to 0 under the Harishchandra homomorphism, then it's going to act as 0 on every finite dimensional representation. And we saw last time in Leonardo's talk that at least in the quantum case, that this means that Z has to be 0, and a similar result is true for the classical case. So that's how one can proceed to check injectivity. The third thing is to check that the image is indeed, that the image of psi indeed lies in here. This argument usually involves some sort of like you define this so-called dot action on the weight lattice, and you define these central characters, and you show that they, at least for like integral weights, they agree on orbits of this dot action, and then from there you can translate this into a statement about S of HW. And then finally, one shows surjectivity. So the reason I'm being really brief with steps 2 and 3 is that in the quantum case, it's pretty similar, and we're going to do something very similar to check injectivity and to show that the image is whatever the quantum analog of S of HW is. However, the surjectivity is kind of the thing that we need to totally retool. So let's just briefly recall how one does surjectivity. So let's just introduce some notation here. So let P of G be the polynomial functions on G. And then, of course, you can always restrict any such function to H. So you get a restriction homomorphism as such. And then this is an algebra homomorphism. And then we can define this group G, which lies in the automorphisms of G. And it's defined by the exponential. It's the group generated by the exponentials of add nilpotent elements. And so, of course, this exponential is well defined because you can just treat it as a power series, and it'll be finite power series. Okay, so G acts on P of G in the usual way. So if you have some if P is in P of G, Y is in G, and G is in the group, then you get an action G dot P of Y is equal to P of as such. Okay, so the key result is the following theorem of Chevalier, which is the restriction theorem. And so the statement is that theta maps the restriction map so let me be a bit clear here. We define an action of G on the polynomial functions on G, so we can look at the fixed point set there, and then H, this can be identified with like that, and of course there's an action of the while group on H tool. Okay, so then what you can do is you can, well, this theorem is proven using go ahead.
The theorem actually says that it's an isomorphism.
Oh yeah, I said that. I didn't, or maybe I didn't say it, but yeah, this is an isomorphism. Okay, and that's actually very important. And so the proof involves looking at traces of finite dimensional representations, which is, I guess, something to keep in mind when we do our proof in the quantum case. Okay, and so then you can use the killing form to identify G with G dual. And because the restriction of the killing form to H is non-degenerate, we also identify H with H dual. And so this theorem rephrased using this identification is that you have an isomorphism as such. Okay, and so now it's kind of looking like the Harishchandra theorem here. I mean, this isomorphism theorem here, but not quite. And so the last step is to show that as a vector space, this thing is isomorphic to the center. So I will not elaborate here, but the point is that this actually shows like injectivity and surjectivity, but the point is that this thing in the quantum world, for instance, we don't have any Lie algebra associated to our quantum group, so this sort of theorem doesn't extend, unlike say the other parts. Okay.
Maybe one should be a bit more precise. So what one shows is that from this vector space isomorphism, that S of G, G invariance is just the associated gradient of Z of UG. And this Chevalier restriction homomorphism is actually the associated gradient of the Harishchandra homomorphism. Okay. Now this is unreadable.
Oh, my bad. This is not.
So the crucial thing which is missing in the quantum case is that we don't have such a nice filtration.
Okay.
So that's somehow what makes quantum case different and more complicated. We cannot just make argument by saying we pass to associated gradient, at least in this form.
Okay. So with that being said, let's move to the quantum groups. So I have reproduced some old notation here. Any new notation I will define, I'll write it out explicitly. But just to refresh your memory, we have the following definitions and notation. So recall the quantum group UQ of G, which is the quantized enveloping algebra over. So now we're not working over the complex number, we're working over our field K. And we'll use U from now on to denote this, fixing G and Q. So recall that it's defined by the following generators and relations. So it has these E alpha, F alpha, K alpha, and K alpha inverse, where alpha is simple. And then the relations are that these K alphas form like this commutative subalgebra. Conjugation by K alpha introduces a factor of Q, and then a commutation relation on the E alpha and F betas. And then finally, the quantized Serre relation. So there's some relations involving the F alphas with F betas and E alphas with E betas. And so because the algebra generated by the K alphas is commutative, we can unambiguously define this notation K lambda, where if lambda is equal to the sum of some positive roots, then K lambda is just the product of the corresponding K alphas with multiplicity. And so this has this abelian group structure, K lambda K mu is equal to K lambda plus mu. Okay, so we'll let U plus denote the subalgebra generated by E alphas, U minus the subalgebra generated by the F alphas. So I should be maybe plural here. And U upper 0 will be the subalgebra generated by K alphas and K alpha inverses. And then we'll let Z of U denote the center of U. Okay, so because these generate U admits this Z phi grading, where we take the degree of E alpha to be alpha and the degree of F alpha to be minus alpha, and then the degree of the K alphas to be 0. And then we can use the subscript notation for any nu in the root lattice. We can define the subspace of elements that consist of purely degree nu elements. And so this notation is somewhat consistent. You may have seen like a weight space notation, because when Q is not a root of unity, conjugation by K lambda picks up precisely a factor of Q to the lambda nu. Okay, so we can also think of U nu as the elements that satisfy this. Okay, so I don't recall if we introduced this last time, so I'll be a bit more specific. We have these two subalgebras, U greater than or equal to 0 and U less than or equal to 0, which are just the algebras generated by the E's and the K's and the F's and the K's respectively. Okay, so since U0 is generated by, has a basis consisting of K mu's, where mu's in the root lattice, and the root lattice is stable under the while group action, we get an action of W, the while group, on U0 just by the most obvious thing, which is this. And then, of course, you can consider invariance in that space. So the new object that we want to introduce is this U not F. And so this is going to be a subalgebra of U upper 0. So that's what this is. And then the Ev condition is that mu is also 2 times a weight. And so so this object here plays the role of S of H in the classical world.
And of course, if is for even.
Right. This yeah. EV stands for even. Okay.
So morally, it's the same phenomenon as various types of representations that appeared in Leonardo's lecture. So since we have kind of more representations, the center is going to be smaller than what you kind of first expect.
Okay. So now we want to, before we go into any proofs or anything, let's try to state the main theorem and kind of the outline of where we're going. So okay, so in the classical case, right, we showed that, or not really showed, but we explained that the the center of the universal enveloping algebra is isomorphic here. And so the quantum analog is a statement about the center of the quantum group. And what we're going to show is that we can produce an algebra isomorphism from the center to this object we just defined, U naught ev, the Weil group invariance. And so this map here, which we'll also call the Harish-Chandra homomorphism or quantum Harish-Chandra homomorphism, is what will concern ourselves with this lecture, and proving the results in this lecture. So the idea of the proof is, as I mentioned, is
before we get to idea of the proof, it would be good to have the statement fully written.
Oh yes, yeah, that's coming. I'll just state it then. So in order to actually state this, we need to introduce some notation. So, but this is just the idea of what's going to happen. So for lambda in the weight lattice, we can define an algebra homomorphism, lambda. So by abusive notation, I'm just going to call it lambda again, from U naught, U upper 0 to your field, an algebra homomorphism. So we're going to define it on the generators, on the basis vectors, by lambda of k mu is defined to equal q to the, where mu is in the root lattice. Okay, and so I think it's okay, yeah, we can show it's algebra homomorphism. It's pretty straightforward, right? Lambda of k mu plus nu is equal to q to the lambda mu plus nu, which is equal to q to lambda mu, q to lambda nu, which is equal to lambda of k mu, lambda of k mu, where nu is also in the root lattice. Okay, so we have this notation. And then we are going to kind of define, so I had a function called gamma in the classical case. We're kind of define the quantum analog per se of that. So so gamma of lambda is going to be a function from U0 to U0 as an algebra homomorphism. And again, it's going to be defined on the basis vectors as gamma lambda of k mu is equal to lambda here, this lambda of k mu times k mu. Okay, so one should notice immediately that gamma lambda plus lambda prime is equal to gamma lambda composed with gamma lambda prime for lambda prime in the weight lattice. Okay, so now recall that U0 is equal to U element of U, where degree U is equal to 0. And so this is, again, as I mentioned, this is everything such that k mu U, k mu inverse equals U for all mu in your root lattice. So so clearly that the center has to sit inside here. Okay, and so just one more definition, or before we can state the theorem. So so we recall by like this PBW-esque looking thing, we have this isomorphism of vector spaces given by multiplication from U minus tensor U0 tensor U plus to U, so this is isomorphism vector spaces. And so kind of like in the classical case, we get this U0, the zero graded piece is equal to U upper zero direct sum of the following spaces. So U minus, so remember that we said that there's a gradation here, so we can look at the gradation on U minus, that's this piece, times U 0 U nu plus. And so one can check that this piece here is a two-sided ideal. And so I'll leave that as an exercise. But again, the point is that we get this map, again, that I'll call pi bar from U0, U lower 0 to U upper 0 given by projection. It's an algebra homomorphism. Okay, so everything I'm doing so far is just doing it in the quantum world that I did at the start. Okay, so that lets us define the
sorry, what's the symbol that you write under the direct sum?
Oh, this is nu.
Nu belongs to Z something.
Z greater than or equal to 0 of the simple. So this pi shouldn't be confused with this pi. This is the fundamental system here.
Oh, it's a simple one.
Yeah, it's just the positive sum of simple roots. So we define the quantum. I don't know if this is standard terminology, but Harishchandra homomorphism, which I'll also denote by psi, because we won't refer to that the classical case again. By composing the projection map with this gamma specialized at minus rho. Okay, and so now we can state our main theorem. Let me leave that on the screen. Okay, so I'll restate our assumptions. Suppose K is a field characteristic 0, and Q is transcendental for the prime subfield. Okay, then the restriction of psi to Z view, the center of the quantum group, is an isomorphism onto its image, which is Q naught F. So this is an algebra isomorphism onto its image. Okay, and so this is what we're going to concern ourselves with. So from now on, I'm just going to write as a remark 1. I'm going to write psi to denote the restriction. So psi, and pi will denote their restrictions to the center, unless otherwise stated. And then remark 2 here is that we have this technical assumption. Suppose K is a field of characteristics 0 over and Q is transcendental over the rationals. We can actually weaken that and just require that Q not be a root of unity. But we won't show that today. Okay.
Arun, you could write this remark down.
Oh, yes. Right. All right. Okay. So
maybe we could pause for questions, and
Right.
meanwhile, I want to make a remark that, well, eventually, perhaps by the beginning of spring, we'll start talking about quantum groups at roots of unity. And the situation there that for the ordinary quantum group, also known as the Concini-Kass quantum group, you can still define the central subalgebra called the Harish-Chandra center. And the Harish-Chandra center is still going to be isomorphic to this W invariance. However, the entire center will be larger. And that situation is very much reminiscent of what's going on in positive characteristic with the classical universal enveloping algebra.
okay, so I'm just going to spend.
Does anybody have questions or comments?
All right, yeah.
So in the classical case, when you took associated graded, you recovered as like Chevrolet isomorphism. In this case, is there some graded version?
I'm not sure.
I mean, there is no grade. There is no nice grading.
But some version of PBW theorem works.
Some version works, but I mean, you kind of instead of the associated graded, you will have quasi-classical limit, which is the algebra of functions on the dual Poisson group of G. And
I didn't hear what you said. Dual what?
Poisson Lie group. So the thing to take home about the quantum group is that it's not really filtered.
Okay.
I mean, there will be a filtration, but kind of, you know, you can declare that, let's see, that E's and F's have degree 1, but then you must declare that K's have degree 0, because these are invertible elements. And your associated graded is going to be, well, kind of, you know, it's not a particularly nice object.
Okay.
Can we make a comment again why we need to take the even part of U0?
So we'll see that momentarily. It's a consequence of you end up getting that the pairing, the co-root pairing mu with the simple roots has to be like -1 to that pairing has to equal 1, and so that tells you that that pairing itself, mu comma alpha check, has to be even. We'll see that shortly.
I mean, that's what I said was that the same phenomenon, that the existence of this other representations. It's not a consequence, but we'll see that the proof actually very closely related to that construction.
I don't know if it's a good moment to ask this question, but so you understand the logic is to kind of work by analogy with the classical case, but as Pavel explained to me long ago, in the quantum case, there is an actually easier way to write down central elements by using the braided structure, by using the trace of commutativity constraint. So it's more like a comment.
Actually, of the square of the braiding, trace of the square of the braiding.
Yes.
Okay, we'll have traces today and braiding in the next talk.
Yeah. So, but another thing maybe worth mentioning is that if we take the formal version of the quantum group, then in some sense this theorem is trivial because so if you can make a completion with respect to the ideal generated by k-1 and right, q-1 equal h bar, so it's a formal version. It's trivial because the deformation of enveloping algebra, so actually, as I mentioned before, enveloping algebra of a simple Lie algebra has no non-trivial deformations as an algebra. And therefore, quantum group as an algebra is the same algebra. And so it will have the same center. And then it's this map is surjective after formal completion. But this doesn't imply immediately that, I mean, this result, for example, it doesn't allow you to see why you need to take the even part of U0. So this result is a little bit more subtle, but in some sense, you should not be surprised that the center survived quantization because of the thing they just said.
Any other questions?
And if I take Q heuristically just to be 1, do I get the classical result? Like, is this result stronger than the classical result? Or we cannot actually do that because it's...
Well, I think the answer to this question is heuristically yes.
No, but also it is yes in the sense that if you we discussed last time that how to degenerate this algebra. So one of the ways is to take a completion, like I say, and then mod out by h bar, by the formal parameter. And in this case, we will recover this result. More precisely, well, I mean, you have to see how you have to get so you have to take this result at the level of values of the Harish-Chandra homomorphism, and then in the algebra itself, you will also get the center.
Okay, with this in mind, I think we can get back to the talk. How about this?
Okay. So what I want to spend a little bit of time on is just outlining what we're going to do to prove this theorem. So let me write proof outline. Okay, so the first step, or first sequence of steps, will be to show that psi is an injective algebra homomorphism from the center to U naught F. Okay, this kind of encompasses the first 3 steps of the classical proof I mentioned. Okay, and then as I said, we need to replace surjectivity because once we show surjectivity, of course, the theorem is proven. So to do so, we have to appeal to a certain, how do I want to say this? So what we want to do is, in order to show surjectivity, is we want central elements whose image is under psi. They'll span U naught F. And so to do so, we're actually going to appeal to the dual space. So U dual is naturally a U mod which is it's dual to the adjoint representation. So you may remember the adjoint representation from previous talk on U. And so it turns out that we can actually, and what we're going to do is we're going to construct a non-degenerate invariant pairing on U. So construct a non-degenerate invariant pairing on U with this suitable field extension. And because it's non-degenerate, it actually gives, and it's invariant, it gives a embedding of U into U dual. Okay, so
well, it would be good to emphasize that it's an embedding.
Okay. Okay, so then in U dual, we can construct U invariants using the quantum trace of certain finite dimensional representations. And so what I mean by that is if you have, so find U invariants in U dual using the quantum trace of the finite dimensional representations. So what I mean by that is you'll have, say, phi from U to and M. That'll be a representation, and you can take the quantum trace of this. Phi will be a map from U to ground field, and we can view the field as a trivial U module, and so then we can ask ourselves what these invariants are, and it turns out that these invariants actually lie. These invariants lie in the image of the embedding. Okay, and so that means since they're invariant, their pre-image back in U is invariant, and then a general fact of Hopf algebras is that invariance with respect to the adjoint representation is equivalent to being central, and we'll show that in the case of U for the quantum group. And then so finally now we have these central elements that we constructed using this pairing, and then we can show that using the under the Harish-Chandra homomorphism, that these central elements we get will actually span. So under psi can produce spanning set of our image. So this will show surjectivity. So as you can see, it's already quite different from what I explained earlier for the classical case. Okay, so
maybe one comment is that this pairing doesn't exist in the classical case. In the classical case, he will be pairing two different things, like the universal enveloping algebra to the functions on the algebraic group or on a suitable open subset in the algebraic group. And somehow, when you do a Q deformation, these things, suitably understood, deform to the same algebra, which is this U of Q, which is, well, just U.
Okay. So.
And also this, well, this what Roman mentioned, the construction using trace of square of the braiding. Actually, it's equivalent to what we're doing here, but it's just a more elegant way of writing it.
But of course, we don't do elegant things, right?
Well, I mean, doing like elegant things requires kind of more theory, and that's what we can do later, probably.
Okay. So the first thing we're going to do is, as I said, show this injectivity and that the image is in this space here. so let's just recall what a Verma module is. So recall the type 1 Verma module.
And Arun, at some point you will want to make a break.
Okay.
And this point is kind of should arrive in the next 5 to 10 minutes.
Okay. Okay. So I think we'll prove a short lemma, and then we can take a break. So we have this type 1 Verma module, M of lambda, where lambda is the weight lattice. You can define it, I mean, just as you do for the algebra. This okay, maybe this is going to become unreadable, so let me. That is the module. I don't know, n, where n is the module u e alpha plus u k alpha minus q to the lambda alpha. Okay, and so we have this lemma, which is that which explains how the center acts on these things. So z and z of u acts on m lambda as a scalar, lambda of the projection map of z. So recall that z of u is in u lower 0, and so this you can restrict the projection map to that. Okay, and then the other part, so this is part A, and then part B is that pi bar is injective on z of u. Okay, so I'm going to leave A as an exercise. It's just like in the classical case. And B, well, this is also kind of like in the classical case, but if pi bar of z is equal to 0 for z in the center, then z is going to act as 0 on all finite dimensional representations. Z acts as 0 because they arise as quotients of the Verma modules. Finite dimensional representations, and then Leonardo proved last time that this is precisely the only element that satisfies this is that z equals 0.
And we take representations of type 1.
Yeah,
we have actually proved that that's sufficient.
Right. Okay. I think it's probably best to stop here for a break.
Okay, guys, let's make a break and resume at 5:05. Meanwhile, if there are questions, please ask.
There was a comment on the center of quantum group is actually easier to find. What is that actually?
Well, I mean, it can be constructed. It's pretty difficult to construct central elements in a universal enveloping algebra. If you ask yourself, how do we actually construct generators or whatever central elements in the center, it's sort of a complicated question. And you can write some construction, as Pavel explains, using the square of R matrix.
Which is basically equivalent to this proof that we're about to hear. So actually here we are actually producing explicitly central elements in some sense.
And from our perspective, it's possible to do because of that invariant pairing.
Right. And so our matrix, construction of our matrix comes from the invariant pairing. More or less, our matrix is the inverse element to this invariant pairing. And so that's why this construction is equivalent to the Dvin-Friedrich-Tiching construction through our matrix, which we mentioned.
In the classical case, the R matrix is trivialized, so you don't see much. Is that right?
Yeah, more or less.
Well, I mean, you can divide by, you know, you can subtract 1 and divide by q minus 1 and take the limit, but that's somehow.
Yeah, this is not going to give you the center from the classical case. So, I mean, you can get the center in the classical case as a limit, but then what happens is you have to combine. So you have a bunch of, for every weight lambda here, you have a kind of central element with leading term corresponding to lambda and for every dominant weight. But these elements kind of all have kind of trivial limit when h bar goes to 0. So to get non-trivial things, you have to take very specific linear combinations of them so that the result vanishes to high order with respect to h bar. And then you should divide by the power of h bar, and then you get some interesting limits. And in this way, you can get all central elements, but the combinations you have to take are pretty ugly and difficult to write down.
Okay.
It's amazing.
That something is going to be ugly. Well, I mean, that's what happens usually.
No, usually everything is ugly. Only something is ugly is exceptional.
Okay, well, I mean, what can I say? Okay, how about we try to continue?
Okay, yeah, I'm ready. All right, so by this lemma, it follows that the Harishchandra homomorphism is injective, because it's, remember, this thing is that gamma minus rho composed with this projection map, and the gamma minus rho is an algebra automorphism. Okay, so now let's see what we can say about the image. So let's just recall some things I defined above. So remember, I defined for lambda and the weight lattice, we defined this algebra by mu is equal to q lambda mu k mu. So which is the same thing as lambda of k mu. K mu lattice. Okay, and then we also have this so-called dot action of the Weil group on the weight lattice given by w dot lambda is equal to the usual action applied to lambda plus rho and then subtract off rho. So it's kind of like rho shifted. Let's see, w in the Weil group and lambda in the lattice. And then let's also recall the action of the Weil group on u0 by wk mu is equal to k w mu, and w in the Weil group. Okay, so we can state an intermediary result, which is the following lemma, which is psi, the center, the image of the Harishchandra homomorphism lies in the W invariance of U0. Okay, so let's see. This one I'm going to probably just state a little bit of the proof and move on from there. So if Z is in Z of U, let H denote psi of Z, which is equal to, by definition, gamma minus rho of pi of Z. And if you remember the property on gamma, this is the same thing as gamma rho of H is equal to pi bar of Z. Okay, now by the previous lemma here, how do I say this? So let lambda be in the weight lattice. Then by the previous lemma, Z acts on M of lambda as the scalar lambda of pi bar of Z, which is equal to lambda of gamma rho of H, as we have defined here. Now, a simple computation by expanding it to basis vectors shows that this is the same thing as this lambda of gamma rho of H is the same thing as gamma is the same thing as lambda plus rho of H. Okay, so kind of like in the classical cases we saw last time, so where we're going with this is we want to show that this is W invariant. So we want to show that this W invariance condition. So we want to show that lambda rho of WH is equal to lambda rho of H for all W and W and for all lambda. So the way we're going to do this is using the fact that you have these, with suitable criteria on lambda, you have homomorphisms between different Verma modules, and that forces the center to act as the same scalar on those. So for alpha and pi, if lambda comma alpha check is greater than or equal to 0, we have this non-zero hom from M of S alpha dot lambda to M of lambda. And so you have to act as the same, Z has to act as the same scalar on both. So this implies that lambda plus rho of H, right? We just deduced that's the scalar that Z acts on M of lambda as, is equal to S alpha dot lambda plus rho of H. But this, if you just expand it out, becomes S alpha of lambda plus rho of H, and then by definition this is lambda plus rho of S alpha of H. Okay, and then you can show this extends in general. You don't need this condition. You can just it holds for all lambda. So that I will not prove, but the point being is that you deduce that for all lambda in the weight lattice, after some work, small work, you get lambda plus rho is equal to lambda plus rho. This should be inverse. It doesn't matter, but S alpha inverse of H, and for all alpha element in pi. So the point is that since the S alphas generate your wild group, this shows the statement that we wanted to show. So we get that lambda plus rho of WH is equal to lambda plus rho of H for all lambda here and for all W in the wild group. And then because a rho shift, it fixes the weight lattice, you can just write this as mu WH is equal to mu of H for all mu. Okay, so in order to finish our statement, which is we want to show that that the image of this thing is in U naught of W, we want to show that,
May I make a suggestion? How about we make this last implication an exercise?
which implication?
That this condition in the last line implies that WH is equal to H.
Oh, okay. Okay, so yeah, as an exercise, this implies, or show, we'll call this star. Star implies WH equals H. And it follows from this linear independence of characters. Okay, so that means that WH is equal to H. Well, what was H? H was the image of Z under the Harish-Chandra homomorphism. So we deduce that psi of Z is an element of U0 W. Okay, so now let's recall exactly what U0 of Ev was. This was equal to the subalgebra of U0. Okay, so now we have the following proposition.
Without W invariance.
Yeah, without W invariance, right? And then we have the following proposition. So the image of psi lies in U naught of W. Okay. I guess I should remark that W also stabilizes 2 times the weight lattice. So this is well defined. So we already know from lemma 2 here that if Z is in the center, then psi of Z is in U naught. So what we can write is psi of Z is of the form A mu K mu, mu element of C phi, where A mu is equal to A W mu for all W in the while group. Okay, and so now what we want to show is that we want to show if mu is not equal to, or if A mu is not equal to 0, then mu is also in 2 times the weight lattice. Okay, so the way we're going to do this is we're going to construct this, use a suitable automorphism of U. So if let sigma from Z, from the root lattice to plus minus 1 be the group homomorphism given by sigma of alpha is equal to -1 for all alpha simple. Now, of course, this is a well-defined group homomorphism because the simple roots form a basis of the root lattice. Okay, and so since we have this group homomorphism, you may remember from last time that sigma induces a algebra automorphism from U to U given by, so induces algebra automorphism sigma twiddle given by, it's just going to scale the generators in an appropriate way. So sigma twiddle of E alpha is equal to sigma of alpha E alpha, which is equal to minus E alpha. Sigma twiddle of F alpha is equal to F alpha, and sigma twiddle of K alpha is equal to sigma of alpha K alpha, which is equal to minus K alpha. Okay, so it's clear then, I mean, it's a very simple automorphism, and it's clear that sigma twiddle preserves U0, U plus, U minus, the center, and the gradation on U. Okay, so our next step is we want to show sigma twiddle commutes with the Harish-Chandra homomorphism. That is to say, sigma twiddle of psi is equal to psi of sigma twiddle restricted to the center. Okay, now, I mean, psi is just equal to gamma minus rho of pi bar, and so if you can show that it commutes individually with each one of gamma minus rho and pi bar, you get this statement. But it's clear that it commutes with pi bar because we said that where is it? Where did I say this? It preserves the gradation here. And in particular, if you write U lower 0 as equal to U upper 0 direct sum those other pieces, everything is stabilized by sigma twiddle and you get, it commutes there. So one just has to check for gamma minus rho, but you can just check this on the k mu's. So you get sigma twiddle of gamma minus rho of k mu is equal to sigma twiddle of q to the minus rho mu k mu, which is equal to sigma of mu q to the minus rho mu k mu, and then this is precisely gamma minus rho of sigma twiddle of k mu. So so we get this commutativity here. Okay, so therefore, if Z is central, and we write psi of Z in terms of the basis, mu element of Z phi, A mu, K mu, then we have psi sigma twiddle of Z is equal to sigma twiddle psi of Z, which is equal to A mu sigma twiddle K mu, which is equal to mu A mu sigma mu. Okay, so since Z is central, sigma twiddle of Z is central. So by lemma 2, this sum also lies in U naught, right? Because Harish-Chandra, the image, as we said, already lies in U naught of W. So what you get here now is that this implies that if you compare coefficients, A mu is sigma mu is equal to AW mu sigma W mu. So this is from W invariance of this thing. And then from W invariance of psi of Z itself, this is A mu sigma W mu. So that means that if you take mu to be, if A mu is non-zero, that implies that 1 is equal to sigma of mu minus W mu. This is for all W in the while group. Okay, and so then you can take W to be simple. And so if W is a simple reflection associated to a simple root, this tells you that, so specialize the W equals S alpha, 1 equals alpha and pi, sigma of mu comma alpha check alpha. Now sigma of alpha is -1, and mu comma alpha check is an integer, so this is, of course, -1 to the, okay, and so this is what I was trying to say earlier, this forces mu comma alpha check to be a multiple of 2. And that shows the proposition, which it should lie in here. Okay, so what we've done now is that we've shown that it's injective, and we've shown that the image lies in here. So the next step is to show surjectivity. And so before we begin there, let's just recall a little bit about the Hopf algebra structure. I'm going to skip mentioning the adjoint representation and the quantum trace. We won't get to that today, but let's just recall what the Hopf algebra structure on the U is. So I'm going to let delta denote the co-multiplication, and epsilon denote the co-unit, and S denote the antipode. And the co-multiplication of E alpha is given as such, F alpha is given as that, and K alpha is given as that. The epsilon of E alpha is 0, and epsilon of alpha is 0, and epsilon of K alpha is 1. And then finally, we have our antipode. S of E alpha is minus K alpha inverse E alpha. S of F alpha is minus F alpha K alpha. S of K alpha is K alpha inverse. Okay, so I hope that's all familiar. So let me make a remark about where we're going. So I'm going to call this bilinear pairing, the bialgebra pairing. Okay, so as I mentioned earlier, we want to construct an invariant form on U cross U. And in order to help us construct that form, we need to construct an intermediary so-called bialgebra pairing on U less than or equal 0 cross U greater than or equal to 0. And so we're going to spend probably the rest of today proving such a pairing exists, and then proving some properties about it. So let me start by defining what a bialgebra pairing is. So definition, X and Y are Hopf algebras with multiplication delta, a co-multiplication delta X and delta Y. Respectively, and a bilinear form from X cross Y to your field, so let's say Hopf algebras over K, is a bialgebra pairing if one x1 x2 comma y is equal to x1 tensor x2 comma delta y of y, and 2, the same condition on the other side, x comma y1 y2 is equal to delta of x comma y1 tensor y2. Okay, and what do I mean by the right-hand side? I should be more specific here. Right. Yeah, so x1, x2, x and y1, y2 element of y. And the form, so this here is, the right-hand side here is a form on x tensor x cross y tensor y. It's just defining it as the product of the individual pieces. So you have A tensor B comma C tensor D is defined to be A C B D, where A and C are an X and B and D are an Y. Sorry, A and B are an X and C and D are an Y. Okay, so I mean, it seems kind of weird, this definition, but it's actually it's pretty natural because so let's motivate this motivation. So a dual is naturally an algebra, and its multiplication is just defined as the following composition. So you take the multiplication map mu star is, well, you want to map from a dual, tensor a dual to a dual. And so the natural, most simple thing you can do is, well, a dual tensor a dual embeds in a tensor a dual. And then you take the dual map to the co-multiplication on a. And this will give you a map into a dual. And then similarly, you can do the same thing for, or I should say, let me call these x and y to be consistent with what I wrote. Okay, and then you can do the same thing for y dual. Okay, and then a bialgebra pairing. Okay, the condition one is the same thing as the map. Which way is it? Is the map that x maps to y dual given by x maps to x dot is an algebra homomorphism. And then condition 2 is this in the other direction. So this is the same thing as the map y maps to x dual given by y maps to is an algebra hom. Okay, so as I said, what we're going to do is we're going to construct a Hopf pairing, a bialgebra pairing. Goal. Construct a bialgebra pairing on u less than or equal to 0 cross u greater than or equal to 0. And so these are naturally bialgebras. They're sub-algebras of U. So, so with that being said, we have the following theorem. Theorem 6. There exists a unique bialgebra pairing, which I'll denote with this, on u less than or equal to 0, u greater than or equal to 0, such that for all alpha and beta and pi, your fundamental roots, your simple roots, excuse me, we have the following equalities. So, and I should add, and mu nu in the root lattice. So k mu k nu is equal to q to the minus nu nu f alpha e beta. Let's write that over here. F alpha e beta is equal to minus delta alpha beta q alpha minus q alpha inverse. So recall that q alpha. So let me write that. So q alpha is equal to q to the alpha over 2. And then the second condition is that k mu e alpha is equal to f alpha k mu, and they're both 0. Okay, so let's prove this, and let's start with the uniqueness. So let's assume it exists. So assuming existence, So this will be kind of just the also help you get a
maybe let's have a little pause. So one can ask why the formulas should be like this, and one of the answers is that what we want is a non-degenerate pairing. So we want a pairing without kernels on the left or on the right. And this will be explained maybe already in the next talk.
Yeah.
And meanwhile, do people have questions? Okay, doesn't seem to be the case. So maybe Arun can continue with the proof.
So let's assume existence of such a form. So uniqueness is a consequence of the fact that it's a bi-algebra pairing, and the fact that here we defined it on the generators. So we defined it on the generators. Then use the bi-algebra properties 1 and 2. So a really short example here that I won't do all the computation now, but just to get the idea of it, let's say you want to compute f alpha, f beta with e alpha, e beta. So then you can use relation 1 here. So let me remind you of that. This relation here. And so this ends up becoming.
Can I make a suggestion?
Yes.
Maybe in the theorem you can label the conditions with Roman numerals.
So yeah, I see. Okay, so this becomes f alpha tensor f beta, e alpha e beta. Okay, and then you can expand that out because the co-multiplication is an algebra homomorphism, and this becomes e alpha tensor 1 plus k alpha tensor e alpha times the same thing including betas. Okay, and then I'm not going to expand it out fully, but because, as we said, we defined the pairing also on the tensor product, this becomes f alpha e alpha times e beta times f beta 1 plus dot 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 plus some middle terms, and then expanding out the last term, it'll be f alpha k alpha k beta, which is k alpha plus beta, times f beta f alpha f beta e alpha e beta. And then you can use relation 2 to split up the product on the right hand side. So I'll just write use 2 to express in terms of the form on generators. Okay, so I hope that's clear about the uniqueness. So now let's actually do existence. So in order to do existence, we're actually going to first construct a form. First construct a form on, you may remember you twiddle 0, but I will remind you. So recall that u twiddle less than or equals 0 is the algebra with the same generators and relations as u less than or equal to 0, except the quantum Serre relations involving f alphas. So what you have is u total less than or equal to 0 is a bialgebra with respect to the Hopf structure formulas that we talked about, and this descends to this Hopf structure descends to a this bialgebra structure descends to the bialgebra structure we have on u less than or equal to 0. Okay, and the reason it's well, I'll get there. So in order to define this form, we're going to define two functions. So for alpha simple, define f alpha in u less than or equal to greater than or equal to 0 dual by, so f alpha on e alpha k nu is equal to minus q alpha minus q alpha inverse for all mu in z phi. And if it's outside of that, then we're going to define it as 0. For all nu not equal to alpha. Okay, and then we're going to define another function, and this will actually this will be an algebra homomorphism as well, from u greater than equal to 0 to k, and we're going to define this as for lambda in the weight lattice, define k upper lambda by k upper lambda of u k mu is equal to epsilon of u q to the minus lambda mu. So mu is in z phi, and u is in u plus. And so I'll just make a remark or an exercise is k lambda is an algebra homomorphism. You can check this actually, I believe, by looking at finite dimensional modules. Anyways.
Well, there is nothing to prove. I think this is just by inspection.
Oh yeah. Okay, so let's actually just not even leave it.
I'm not quite sure how this is relevant.
Well, it's relevant in the sense well, I guess, okay, let's not pursue that, and we'll just leave it at this. Okay, so we have the following lemma, which is where we're going to construct the form, which will help us construct the form on u twiddle less than or equal to 0 across u greater than or equal to 0. So the map f alpha maps to f alpha, and k mu maps to k mu, alpha simple and mu in the root lattice defines an algebra homomorphism from u twiddle less than or equal to 0 to u greater than or equal to 0. Okay, and so the proof of this is left as an exercise, but I will remark that it's pretty straightforward, as u twiddle less than or equal to 0 behaves kind of like a free algebra in the sense that the f's have no relations, and the relations involving k mu are easy, and that's why you kind of need the fact that these k lambdas are algebra homomorphisms. That's where this comes into play. But again, it's easy to define on this map on U twiddle less than or equal to 0. And so by our definition of the bialgebra pairing, what we get is, so I'm just going to put a box here. Therefore, this algebra hom induces a pairing, which I'll also denote this way. Greater than or equal to 0 to k, satisfying x1, x2, comma y is equal to x1 tensor x2, comma delta y for all x1, x2 in U twiddle is equal to 0 and y in U greater than or equal to 0. So we notice that it's not necessarily a bialgebra pairing because we haven't checked the other side, but we do have one side. And so that's what we check in the next lemma. So lemma 8. So this pairing also satisfies satisfies on the other side, y1, y2 is equal to delta of x, y1 tensor y2 for all x in U twiddle less than or equal to 0 and for all y in y1 for all y1 and y2 in U greater than or equal to 0. Okay, so the proof of this is a computation. You can check directly on the generators. Actually, just on the generators, excuse me, you can check on just the generators of U twiddle less than or equal to 0. The computations work out by taking an arbitrary element in U greater than or equal to 0, and you can inspect on the generators. For instance, the easiest one, if x equals k mu and y1 and y2 are arbitrary, then you get x comma or k mu.
Excuse me. The status of the first statement you made is that this check, so it's enough to do this check when x is one of the generators of U tilde less or equals than 0. So the general case reduces to there.
Correct.
These are the statements that you are making.
Yes.
And should I understand that this is a general thing about Hopf pairings or bialgebra pairings? What is the generality for the statement?
I think so. I mean, it's to check something as a Hopf pairing, it's enough to take element which you're generating.
But this somehow should use the properties that we have already established. Otherwise, we are checking something out of nothing, it seems.
So maybe I can work out an easy example and then.
Well, let me make this suggestion. So it's not that we have much time left. So maybe you put what you plan to put, and then you write a sketch of that argument in the nodes, an argument which will deduce this identity on arbitrary x from this identity on the generators. How about this?
Okay.
Okay, that's one. And by the way, this u tilde less than 0 should be u tilde less or equal than 0. Yes.
Okay, so so just as a very straightforward example, since k mu is probably easier to work with, so this by definition is k upper mu of y1, y2, and I said it's an algebra homomorphism. So y2, which is k mu tensor k mu y1 tensor y2, which is equal to delta of k mu y1 tensor y2. So you can kind of break things up using the generators and this by this property here, the conditions 1 and 2 of a bialgebra pairing. So the remaining things were left as an exercise, but I guess it is now left to me as an exercise. Okay.
Well, we shouldn't discriminate the speaker when we distribute exercises.
Okay. Okay, so the point is that, okay, let me, how much time do we have left here?
Somewhere between 5 and 10 minutes.
Okay.
And it's at your discretion.
Okay, so let's, what we get out of this is combining this lemma 7 and lemma 8 is we have a bialgebra pairing on u tilde less than or equals 0. Okay, and so the point is, can we descend it to u greater than or equals 0? And that means it should vanish on the Serre relations. And so in order to show that, we need to just make a small observation first, which is the following lemma. So for all mu nu in the root lattice, with mu not equal to nu, we have the pairing. So let me say it this way: if x is an element of u minus mu, and y is an element of u plus nu, then x paired with y is 0. And this is the proof. This is just a direct consequence of our definition. So let me just, where did we define it? It's just a direct consequence of the fact it's an algebra homomorphism, and then we defined it to be defined as such. Okay. So with that being said, we want to check this on the Serre relations, and I think we'll end after that. So what we want is, so how should I say this? Okay, so in order to show that this form descends to a form on u less than or equals 0 across u greater than or equals 0, the Serre relation, the elements that form the Serre relations, the u alpha beta minus, where alpha and beta are not equal to each other and are simple roots, defined by the following. So I won't explicitly, so we talked about this last time, so I'm not going to explicitly recall what exactly all these notations are. It's not too important. But the point is that these elements should lie in the left radical. Then we're free to take whatever preimage in U tilde and just and we can, the form is well defined on U less than or equal to 0. Okay, and so indeed we have the following lemma. And I think we'll end with this lemma 10. U alpha beta minus x is equal to 0 for all x in. Okay, so the proof is, so we're going to appeal to lemma 9. By lemma 9, we need only look at the pairing restricted to did I define R? I did not define R. R is equal to R alpha beta, by the way, is beta comma alpha check. And so you can, just by inspection, you can tell that this element U alpha beta, yeah, 1 minus that, excuse me, 1 minus that. Yeah. So you can tell just by inspection that the space, that U alpha beta is homogeneous, and it lies in minus this many alphas plus beta. So that's where we get this. So cross U R alpha plus beta plus. Okay. So this is straightforward for, so I mean, I'm not going to prove this in generality, but we will do an example for A2. So for A1 cross A1, so what I mean is when G is of type A1 cross A1, this calculation is straightforward. So the next kind of case is when G is of type A2. And then I was told that the general case, to leave the general case as an exercise was cruel. So
especially in type G2, I think Janssen does provide some computations along these lines, but we shouldn't show them.
Okay, so so in the type A2, in A2, we have you have two choices for alpha not equal to beta simple roots. By symmetry, you can just pick one of them. So we pick one, and in A2, so of course, this R alpha, the co-root pairing will be -1, and so R alpha beta will equal to 2, and so our element U alpha beta minus explicitly is 2 choose 0 alpha f alpha squared f beta.
Maybe we should just write that the coefficient is 1. So, well, let's write it down. So the first coefficient is 1. So let's just write it as such. So it's f alpha squared f beta minus
yes, minus
q plus q2 minus 1
q alpha
q alpha it doesn't matter because both roots are the same. Well, it's a plus. It's a quantum 2.
So,
Arun, this is a quantum 2.
Sorry, what just?
The coefficient is quantum 2. In the usual cell relation, we will have 2.
Oh, yes. 2 choose. So yeah, it's just quantum 2. Okay. F alpha, F beta, F alpha, plus F beta, F alpha squared. And a basis for U plus 2 alpha plus beta. So there's another Serre relation on the other side. So U twiddle plus is 3-dimensional, but the Serre relation kills off one of them. Oh, not 3-dimensional, but like modulo the K mu. I guess it'll be clear when I write it. Is E alpha squared, E beta K mu, and E alpha, E beta, E alpha K mu. Okay, and so the point is that we're going to pair this with these and these, but you can just ignore the K mu's because they're not going to contribute anything in this particular case, and in general, they only contribute a factor. So it's really, we're just looking at this, and when you do the computation, when you pair the two, you get 0. So when you pair with the basis on, and you get 0, then in general, it's going to vanish on the Serre relations. So the point being is, if you apply this lemma, this descends to a pairing on U less than or equals 0 cross U greater than or equals 0. And that proves the theorem. Okay, so let's end there. Are there any questions?
Yeah, so I forgot the formulas for the pairing, but is it the case that if I restrict this pairing to like the E's and F's and K's, and then I take Q to 1, I would get something familiar, like the killing form or something?
I don't know, maybe.
The answer is no. Because you don't have any pairing on the universal enveloping algebra in the classical case.
Yeah,
what
that's why I
get
the G, like the E's, just the E, F, and K though.
What you do get, you will get a pair, something like a pairing, let's say, between U of n minus and functions on n minus. And this is a usual pairing where you apply an element of the universal enveloping algebra to a function on a group and evaluate at 1.
But I mean, yeah, I do. You have a pairing on U times U, right?
No. Well, I mean, what is U? If U is a universal enveloping algebra, then yes. Quantized universal enveloping algebra, then we do have a pairing.
Yeah.
We don't have any pairing on the classical universal enveloping algebra.
But won't it restrict to a pairing on like G times G? Or a pairing exists, but my question is like, what does it have any significance? Maybe.
Well, I mean, that's maybe Arun can show the formulas for the pairing. And so, of course, the easy thing that you can do is recall that Q is, the formulas were above.
Oh, these?
Well, I mean, the statement of the theorem. Yes, here it is. So, of course, you can say that Q is e to power h bar, and K mu is something like, well, I mean, it's a little bit awkward, but it's something like Q to power mu, although this doesn't really make sense. You need to be a bit careful. And if you want to think about it this way, then yes, you will get something like the restriction of the invariant form to B minus and B plus. However, the point is that somehow this never extends to the pairing between the universal enveloping algebras. Tony, does this answer your question?
Well, yeah, so I think my question, and maybe it doesn't make sense, is after you extend it, I can then restrict it to like the vector space generated by the E's, F's, and K's. Right.
Well, in K's are gone because those were exponential. So you will have some. Let's say, well, I mean, you will need to multiply this pairing by, you know, by this denominator that we have. Then in the limit, you do get something familiar. Although this something familiar is not going to be particularly useful.
Okay, and what is it?
No, just the restriction of the killing form or something like that.
Okay, okay.
I mean, you see that F's and E's pair as needed, and Q's and H and H is also paired as needed. Because you have Q to power to the right power, essentially.
If I may add to what you're saying, Ivan, if you see for Tony, one way to make things look more difficult to specialize to Q goes to 1 is to pair U greater than or equal to 0 with itself. Then you really see you're pairing an E alpha and E beta. I mean, you can see that you will have difficulties. I mean, this will degenerate when you restrict, when you try to specialize Q goes to 1. This is not something that there is no interesting pairing on the positive part of the enveloping algebra.
Oh, and you're saying it's non-zero in this quantum thing, those pairings?
It's a non-degenerate even. You see, U less than or equal to 0 is isomorphic to U greater than or equal to 0. Okay, these two, the negative and positive part are isomorphic. So you could as well have define the pairing on U greater than or equal 0 times U greater than or equal to 0. You can forget about the case, even strictly positive in both parts. You take the same formulas, and then you really see that there is a problem in specializing. And I mean, a point which has been mentioned before is that U strictly positive, once you go to functions of Q, the field of functions, is essentially a self-dual Hopf algebra. So, and that has to do with this pairing, this non-degenerate pairing, and this is completely fair, of course, when Q goes to 1 in the classical case.
Right. So the explanation should be that you know, when this pairing is non-degenerate. In some sense, it's a perfect pairing. And of course, when when you have a perfect pairing depending on parameter, and you specialize this parameter, the pairing may fail to be perfect.
Okay, but there's something which you before.
You see it perfectly well because the dual algebra of U of n is the algebra of functions on the group. That makes sense?
But you're saying if I extend this pairing to the full universal enveloping algebra and then restrict it to the positive part, it's still perfect?
Well, yeah, that's how the pairing on the full universal enveloping algebra is going to be defined, essentially. Up to some multiples of Q, which are always there. Okay, guys, are there more questions?
Maybe a comment if you allow. So I think one can probably give a computation free proof of part of this theorem by using the fact that the positive part can be realized either using quiver algebras or for particular values of parameters using perverse sheets, because then the pairing is natural.
Well, I think an easier way will be just to go with the original construction of Dringfeld, from which this pairing is kind of manifest.